Good. Okay, so yeah, let's just begin. So I'll begin with an introduction. I think most of us, most of the people in this audience must be experts, but it's still good to remind us, sort of some remarkable things about finite temperature physics that you can learn from holography. And so let me just begin with a very brief introduction, though it's very elementary. It just helps us to set the stage. So the ADS CFT correspondence relates physics of gravity in asymptotically antidesiccant spaces to physics of conformal field theories. And let us just briefly sort of set up the stage by looking at a prototype example of antidesiccant space in 5 space-time dimensions. And here is the metric, which I think all of us are familiar with. Here R is the radius of ADS5, which determines its curvature. And this is a 3-dimensional sphere, and the time, and this is the radial direction. And one of the things to recall is that when you take R tends to infinity, which is the boundary of the space, the metric is of the structure. And basically, this term drops out, and it becomes minus dt squared and this d omega. So it becomes R times S3. So the metric is conformal to R times S3. So this is the boundary of ADS5. And by the ADS CFT correspondence, this conformal field theory on this particular space is related to the string theory, actually. I mean, that's the full power of the duality on ADS5. Now, this duality, just like all other dualities, is a strong, weak duality. And just to sort of recall, the parameters involved in the duality are the following. There's a G Newton's constant on the gravity side, and the radius of ADS on the gravity side. And on the CFT side, there is the SUN gauge theory. So there is an N, the dimensions of the gauge group, and the Yang-Mills, G Yang-Mills. So here is sort of the dictionary which relates the parameters. On the red is basically the gravity, and the green is the CFT. And you can see that if you measure the radius in some fundamental scale where the theory is coming from, here it is the string length. If you measure it in units of that, it's related to the square root of the 't Hooft coupling. And if you measure the Newton's constant in the units of radius of ADS, here in 5 dimensions, the Newton's constant has dimension 3, and I mean length dimension 3, and it is proportional to 1 by n squared. I've skipped factors here. So what this tells us is that a classical 2-derivative gravity, Einstein, is a good description, meaning the higher curvature terms are dropped if the 't Hooft coupling is very large. And you can trust classical gravity when n is large. So the field theory in that limit in which you can handle gravity is strongly coupled and at larger. Now, given this field theory description of gravity, the first most natural question one can ask, in fact, it was asked immediately after the ADS CFT correspondence was introduced, is what is the description of one of the most well-studied solutions in gravity, which is the black hole. So there is a black hole, the Schwarzschild black hole, the simplest form of black holes in ADS5, and the background is still asymptotically R times S3. You can check that by taking the R goes to infinity. But if you take this at finite temperature, if you consider this for the Euclidean theory, the temperature direction is identified with the periodicity of the inverse temperature. I mean, the time direction, sorry. The time direction is identified with the periodicity of the inverse temperature. And therefore, and this happens in gravity also. There is some point, I think all of us are familiar, there is a conical singularity which you have to remove, and the periodicity comes naturally at the temperature of the black hole. And therefore, the thermodynamics of the black hole is dual, has a dual description in terms of conformal field theories on S1 times S3. So that's the reason this geometry is interesting. Conformal field theories on S1 times S3 is naturally dual to black holes in ADS5 or lower dimensions if you sort of look at gravity in lower dimensions. Now, it's just as, I think, just to recall the power of these correspondences, not just thermodynamics, even transport coefficients in conformal field theories can be evaluated from its holographic dual description. Using gravity descriptions, we can evaluate conformal field theory transport coefficients. But of course, because of the dictionary of the parameters, the gravity description is valid at strong coupling, strong 't Hooft coupling, and at large n. And therefore, using the gravity descriptions, you can get very interesting predictions for field theory. And these are regimes of field theory which are inaccessible. And let's examine some of the surprising sort of quite non-trivial results which are still open, from the field theory point of view to sort of understand. So here's one. The expectation value of the energy density for an electrically charged planar black hole. It's a charged black hole. Planar, meaning the horizon is a plane. In Einstein-Maxwell's theory on IISc, if you sort of look at the thermodynamics from the gravity perspective, the mu is related to the charge, the chemical potential. So we have written this whole energy density in terms of field theoretic parameters. I mean, it is actually derived in gravity, but it is written in terms of, as though it's a field theory. So you get the conformal field theory description, T cubed, that structure, but note the way the scaling goes is not just like a typical field theory. And there is this series, and each of these numbers are precisely known. And of course, this predicts something about strongly coupled CFT of the M2 branes at finite temperature and chemical potential. This is not as familiar, but still it's quite surprising, this result. Here's a more familiar one, n equals 4 Yang-Mills. At weak coupling, we know how to sort of figure out the thermodynamics because it's free theory and it goes as n squared. Of course, there is a prefactor which can be fixed by studying free gases. But at the holographic dual, if you use, this is at strong coupling, there is a difference of factor in between, and this, of course, hasn't been explained still. More recently, I think this is another sort of interesting results for thermal physics. One-point functions of operators of large dimensions, in CFTs, which admit ADS duals, have been computed again using the gravity description. So what one arrives at is this particular formula. So at large dimension, when you just sort of analytically continue, there's a phase which develops in the one-point function, and the phase contains the proper time of the particle when the particle is released to the horizon to fall into the singularity. So it's an information, from gravity, which has been calculated actually from information of geometry outside the horizon. But this phase is some little information about geometry beyond the horizon. And this is the length from the boundary to the horizon. So this was first observed by Maldacen and Grinberg, and with Srijan, we had sort of found more examples of this phenomena. In fact, there is a generalization which we had shown, which Maldacen had predicted, but we have shown explicitly, is that if you have the horizon with outer as well as inner horizons, I mean charged black holes, which have both inner and outer horizons, then there is the time, this imaginary part contains the time the particle takes to fall from the outer horizon to the inner horizon. L is the length from the infinity to the outer horizon, L hor. And then there is a singularity from the inner horizon to the singularity. So there are three lengths, proper lengths, and all of them are there in this information. And this thing is coming out of the gravity calculation. And of course, it is very, it's very sort of provocative to think about this from the CFT and see if at all one can understand it. And actually, that is what motivated us to get into all these problems to study CFT one-point functions. So such results motivate the study of field theory properties at large n and large strong coupling, because it gives us information about the geometrical properties in gravity. And And in fact, the second class of results, the results about one-point functions, show that even horizon, simple properties of the horizon, can be understood by studying conformal theories, field theories at finite temperature. Now, but the difficulty with this sort of projects and so on is that very few theories, there are very few theories whose finite temperature properties can be understood at strong coupling and at large n. Very few theories. I mean, and the methods are not at present not strong enough. But a class of theories in which is tractable is the Owen model with the quartic interaction and the Gros-Nouveau model with quartic interaction. Chern-Simons theories with bosons and fermions, for which a lot of work has been done. So such theories are tractable, and one can try to sort of address such questions in these. So such theories also, not just from holographic point of view, such theories are also relevant to condensed matter. In fact, the Owen model is used to describe the critical points of Heisenberg magnets. That's how it was introduced that way. And in fact, just the Owen model has even more relevance in holography. The critical point of the Owen model, the non-trivial critical point of the Owen model at large n, and its strong coupling is conjectured to be dual of higher spin theories in ADS4. I mean, this is not two derivative gravity, but more sort of esoteric theories in which there are arbitrary spins. So in fact, you get information about that. So, and as I said, this higher spin theories are extensions of Einstein's theory of gravity, which contain an infinite tower of particles of higher spin. And they're toy examples of string theory, which also contains higher infinite towers of spin. And therefore, it is interesting to study the Owen model at finite temperature to get some hints about the thermal aspects of higher spin Vasiliev theory. So that is one of the motivation, because there's a solvable models as well as you get information about higher spin Vasiliev theory. But furthermore, as we discussed, when the geometry is placed on when the field theory is placed on such geometries S1 times S2, this is a geometry which would have corresponded to that if there was a black hole. And in fact, when the theory is gravitational theory is Einstein gravity, one of the first things people did for this is to study various classical solutions which asymptotes to S1 times S2, for instance. And from there, one can infer if there is a phase transition or not. And in fact, in Einstein's gravity, Witten argued that there is a phase transition, and it's called the Hawking page. But it's not clear that in higher spin it is there. And one thing one can understand is studying this partition function of the Owen model, one can hope to see if there is something like that. Or maybe it is suppressed, but how suppressed it is, and so on. So in spite of this extensive studies of Owen model, I mean, Owen model has a rich history. It has not been studied systematically on this particular geometry. And this is, of course, the geometry relevant for this possible transition. So, and this, this and the other questions which I said before was one of the reasons I got motivated in this direction. And so in this talk, what we will do is basically present this, this main result. And if there is time, maybe I can talk about other things. But I hope I can, do a fair job of this result. So we will develop a method to calculate partition functions and thermal one-point functions of higher spin. As I said, it has a higher spin symmetry. Thermal one-point functions of higher spin operators of this model, critical Owen model, it is a strong coupling point at large n on this particular geometry. And this method results in a systematic, large radius expansion or high temperature expansion of the theory in S1 times S2. So let's just go ahead into the model now. And I think many of you might know how it is solved, but I will just recall it, I mean, just to have an idea. So you start, this is a simple, the model is quite simple actually. I mean, you have this, phi I mean, real scalars and n's real scalars in the fundamental with a quartic interaction. So this is the quartic interaction. And the metric, and now we, instead of just on S1 times R2, we take it on S1 times S1 because it's identified times the sphere. And to evaluate the partition function, we'll follow the standard methods. So the standard method involves actually linearizing this quartic interaction. So we have this quartic interaction, and one linearizes it by something, I mean, it's known in the literature as Hubbard-Stratinovich transformation. Essentially, it's a Gaussian, integral. So you introduce an auxiliary field of this kind. And if you do the integral over zeta, as it is written here, if you do the integral over zeta, then you can imagine completing the squares, and you will actually get the quartic interaction. So once you cast it in this language, you can actually see by large n counting that it's only the zero mode which of the auxiliary field that contributes at large n, at the leading large n. It's only the zero mode which contributes, and all the non-zero modes are of the zeta, the auxiliary field, are suppressed. And therefore, you can treat this as a mass, you can treat the auxiliary field as some mass squared, just keep it as a parameter. And once it is done as that, so it's only the zero mode, then you can imagine once you keep that as a mass, and so this is a massive scalar. And then once you find that partition function, you can do a saddle point to do the zeta integral. So that's the strategy. So you treat that as a mass, and so you have a partition function of a massive scalar. And then once you evaluate that, you perform the integral over the zero mode auxiliary field by a saddle point method. So here it is. So and then when you do that saddle point integration, there is when all saddle points have a minimization equation, and that leads to the following saddle point equation. So if you take this as the partition function of the massive scalar, and then you have to, if you plug it inside and you look at the equation for the zeta, and zeta is identified as m squared, you will actually get this equation for the saddle point. Now you're also looking at large lambda limit. So we are looking at large n. Large n is what allowed you to focus to the zero mode of the zeta, and large lambda sort of focuses, brings you to this, you make it zero, and you get this particular equation, which is called the gap equation at lambda equals 0. So the strategy is simple. Strategy of method of obtaining the partition function of this theory at large n and large coupling is the following. Evaluate the partition function of the massive scalar on S1 times S2. If it was R2, which is commonly done, S1 times R2, but here we are trying to do S1 times S2. So you evaluate the partition function of the massive scalar on this. So that's a function of mass and a partition function. And then you solve, you look at this equation and solve for MTH, plug it back inside, and that's the partition function at the critical point. So for S1 times R2, the solution, it has been done early in the 90s, I think, 90s by Sachdev actually and collaborators first, and then he found more properties later. So what is the solution of the gap equation is the logarithm of the golden ratio, I think it's called. Once you, we will see this we'll see this as we go ahead when you do it on sphere. So this was the solution found. And then when we substitute it back into the partition function and extract the energy density, you get this typical thermal CFT structure, that energy density goes as T cubed, and there is this nice zeta function which comes about, and there is a factor in front. And if you sort of compare it with the that non-trivial fixed point answer with that of the massless boson, which is lambda equals 0 and MTH equals 0, the trivial theory, the Gaussian theory, there is a ratio very similar to the n equals 4 Yang-Mills, which has not been explained. There's a ratio by 4 by 5, but here, of course, we have a calculation method for this. Now, so what we would like to do is basically extend this thing to S1 times S2. And for this, we evaluate the partition function of a massive scalar on S1 times S2. So the strategy was that we have to evaluate the partition function of the massive scalar and then minimize that partition function, find the thermal mass and plug it back inside. So, so though this question, okay, just this question is quite simple, which maybe you can ask even in the quantum field theory class. What's the partition function of a massive scalar? And it seems quite trivial on S1 times S2. The question seems trivial, but we could not find a good expression, of this in the literature actually, and so we sort of do this. We follow this strategy. So, so I'll try to break this down in steps. So if you look at the of a massive scalar, so so the action is basically the Laplacian plus this mass squared, right? Now it's on S1 times S2. So the Laplacian, I mean, when you do this integral, the determinant, log determinant becomes log of that, eigenvalues, sum of the log of the eigenvalues of the Laplacian. And the Laplacian, because it's S1, in the S1 direction, it's all the Kaluza-Klein modes, the Matsubara frequencies, basically. And on the sphere, it's L1, L into L plus 1 by R squared, the Laplacian on the sphere. That if you complete squares, you can rewrite it in this fashion, actually. L plus half the whole squared by R squared. And this is the degeneracy of the, of the modes on the sphere. So it's simple. I mean, this starting point is quite simple, and anybody can understand it. For instance, in flat space, it's log of p squared plus n squared. Yeah. So, and you have to sum over the Matsubara frequencies and sum over the angular momentum modes. So that's the answer. But of course, you have to do the sum and try to get an answer. Now, the Matsubara sum, there are standard techniques of doing this, basically using some contour deformation techniques to do the sum. And if you do that Matsubara sum, that is well known in the literature actually, and you will get this expression: log of z is equal to this particular. There is this term, and there is this added term. Almost, I mean, you see the Bose-Einstein structure coming out. So that structure comes out. This is from, roughly speaking, sort of the zero modes, but not exactly. But anyway, it's like taking one exponential out, and the log that will come out actually, and this organizes into the other term. And so there are two terms in this partition function, and the difficulty you can easily see. The difficulty now is essentially doing this angular momentum sum. It occurs in the square roots. It occurs inside the logs and so on. That is difficulty. If it was flat space, it's basically a momentum integral, which is tractable. So that's the difficulty. Now, so I will illustrate this method just from the first term, and the same method is done for the second. Similar steps are done for the second term. So let's look at the first term. So we first regularize it. We do so that is, I said. So our goal is basically to write this whole thing, do the L sum, and write it as an expansion in terms of 1 by r, a series in 1 by r. R is the radius of the sphere. So let's take the first term. We put in minus alpha just to regularize it, and and when you put alpha equals minus half, it becomes that. The term which we're looking at. So the first step is to make this exponential. So so that using a Schwinger trick, using the typical gamma function Schwinger trick, you can make it exponential. So this is a standard trick in which once you do this integral, you will wind up getting this. So introduce this integral to get this extra term. Then then of course this L into L plus 1 at least has become into the exponential. But then it's still pretty hard because L plus half the whole squared is there, right? And that is sort of the trick. The next step is to do that sum basically. And this trick, I mean, I'm following the same steps that would have been that we followed for that is followed in the literature for momentum, except that it is this key step of doing this L sum, which is sort of new. But the step is actually very simple, and I don't know, I didn't find it in the literature before, because I think it has been this key little step has been actually, we imported it from a series of work which I've been involved in another direction. So I will mention it. So it's basically to linearize that sum. So this sum you can linearize by introducing yet another integral. So here's it's a sort of Hubbard stratum, which is just for the integral. So if you look at this integral, there's a Gaussian integral here, u squared u, and then if you complete the squares, that means if you complete this Gaussian integral, if you do this, you will get the L plus half the whole square. So this exponential term, essentially is linearized by introducing a Hubbard-Stratanovich trick. And then once you have it in this form, you can easily imagine the L plus 1 by giving a small imaginary part to u. You can easily do the sum over L. So that is the trick, actually. That's a simple trick. And but this trick is this trick which has been recently been done in many other contexts. If you see the papers, you would see that. So it has been initially introduced by these authors. We have also used it for several works, actually. It was done for conformal fields, actually, on spheres, to cast these partition function of conformal fields on spheres as integrals over something known as Harishchandra characters. But these are for conformal fields, and here this is that we have imported for this massive case, actually. So once you do that, once you do the L sum, okay, let's go back slightly. So you can do the L sum, which is basically a derivative of the geometric kind of series, and that becomes derivative because of the 2L plus 1 in front. So that becomes this, and now we can do the tau integral, which basically results in a Bessel function, and we arrive at this particular fact. And you can you can find some evenness property and convert it into this particular integral. So that the difficulty of summing over L is over. And then, but we still have this expression in which there's a Bessel function and there is this integral. You can integrate by parts and make the derivative hit on the other side, and we get this. Now, this form is actually the nice form. Once you have it in this form, you have this u by r, and at large radius, you can do a expansion of this sign, 1 by sign, in terms of Bernoulli numbers. So that is the expansion. It is known, how to do 1 by sign in terms of Bernoulli numbers, and Bernoulli numbers times the power series, whose coefficients are Bernoulli numbers. And so that expansion is fed in, and then each of these integrals can be done term by term. So that's this, and finally you can go back and substitute alpha equals minus half. Yeah, so a lot of tricks. So, but then we'll have to do some checks, and I will describe the checks soon. So performing similar tricks for the second term, you recall that there were 2 terms in the partition function, and if you do the similar tricks for the second term, you can organize this whole thing as this form. That's also interesting, actually. We can organize this in terms of polylogs, actually. And in fact, at high values of these things, at p, it becomes, negative p is there. Sometimes it's negative, but that is understood as polylogs which truncate. So anyway, it can be organized in terms of a nice series which involve polylogs. And in fact, for the theory free boson on S1 times RD minus D, on S1 times SR2, it was first, this polylog structure was observed by Sachdev. And in general, for the massive free boson, for S1 times RD, it was observed by Petru. So let's look at the structure. So if you expand this out, as a power series, you can see the power series 1 by r structure here. You see this? Yeah, this is the 1 by r structure. Uh, uh, and if you expand it in terms of 1 by r, this is the first term which is familiar, which everybody know. I mean, which people who do this model on S1 times R2 know. This is the first term in its partition function. You see it is extensive. R squared, the green is the first term, it's extensive. And then there are, here is a 1 by r kind of systematic expansion in 1 by r. And at each order, as expected, there is a function of beta by, in beta by r, there's a function of m tilde beta, right? So it's still not a conformal theory because there is a scale m tilde beta, extra scale m tilde beta. So it's just a partition function of a massive scalar. Now, before we go ahead, because we did so many tricks, we will do 2 simple tests actually. One is before you perform the expansion in beta by r, we take the massless limit because that is something which people have studied extensively. And so we take the, which is known, I think, no, not extensively, which is known. So, if we take the massless limit, the first term, you recall there were 2 terms in the partition function. The first term becomes 0, actually. If you do some regularization, it becomes 0. The second term organizes in this fashion. I don't know whether we can immediately see it. Let's see. I don't know. Let's go back. Second term, yeah, it takes some effort because so m equals 0. The square root can, once this is 0, for instance, this square root goes away, and it sort of becomes simple, and it can be written as the following form. It becomes this, and then after doing this integral, you can do the integral, and it can be written like this. And this form was known by Chang and Docker in 1992. They had this particular structure for the partition function. So it sort of satisfies that. But the new thing is that after the beta by r expansion, can we actually see whether it matches with expansion for the massless theory? So now one of the things is that when you take this massless limit and the expansions we have, right, you can see from here itself. You see there is a m beta power structure coming downstairs, because when m beta is put downstairs, there is this m beta times m beta. So this becomes 1 plus m beta, and then so there is a power m beta coming downstairs, and we are taking m beta to 0. So there are this whole series of terms which come about. And then there is a beta by r kind of terms, and then there's order m beta. So these are things which we can throw. But there are these sort of singular terms which are coming in, and which seems quite strange. It's not strange. It seems remarkable how it will organize itself. But it's a whole series of terms which come in. And it can be written. The general form of the series of the terms can be written actually from the way it is. It can be written in terms of Bernoulli numbers from where it has come itself. Now this whole series of terms, though it is it is 1 by m tilde r, you can do a Borel sum. And we have done this Borel sum. It involves some techniques, details and manipulations. It's there in the appendix of our paper. But we can do a Borel resummation of this whole series. And when you do Borel resummation, the leading terms after you do the Borel resummation in the m tilde. So it's basically an analytical continuation of once you do the Borel sum, and it can be done perfectly, and it leads to this particular form plus order m beta term. So there is this green finite terms, except for this log m beta, and then there are order mr terms which can be thrown away when the m going to 0 limit. M tilde and m are the same. I don't know, there's some notation issue. So if you introduce that back inside, so this m, so you remember, let's go back. So there is a log of beta m tilde here, and once the Borel sum comes, it is log of m tilde r. So together the m tilde cancels. It's so nicely organized that it m tilde cancels, and then it is just this green term, and it's all finite actually. Rest are all finite. So the whole, the green set of terms which were looking singular after Borel sums become nice, and it is this term. And remarkably, I mean, if you compare this expression with that of the conformal coupled scalar, meaning the massless scalar on S1 times S2, this expansion is given in this paper, recent paper of this group, and it precisely agrees actually. So it's a good check. It's really a good check that all these manipulations, which which involve various tricks of integrations and so on, it sort of it passes this check. Now let's proceed to the next step. So we have the partition function of the massive scalar in terms of in terms of the polylogs, and the next step is basically minimize that with respect to the mass, so that leads us to some equation, the gap equation, which of course, once you minimize, you can use certain differential relations of that polylogs satisfy. You can recast it in some way like this. But what happens, if you just want to see a feel about it, so if you expand it in terms of 1 by r, so there is the leading term, and then there are these suppressed terms. So therefore, you have to solve this equation, gap equation. This is sort of the iterative part. Here we have all exact fully, like as a series, at least we have the full term. But here we have to solve order by order to get the next term. So like you have to solve this transcendental equation first, which admits that solution in terms of the golden ratio, log of the golden ratio, and then feed that back inside and keep finding iterative corrections. So this gap equation can be solved order by order and beta by r, and these are the first few terms. And here, yeah, this is, for instance, the what Sachdev had found, and these are the corrections to that as 1 by r expansions. So now we've plugged that back into the sort of expression for the partition function, and we can plug it and get an order by order expansion. Of course, we didn't go further. We got till here, but in principle, it can be done. Actually, we are thinking of doing it at higher orders to see if there is any structure. So we can sort of get the expansions, and of course, the energy density. And the energy density has that structure, the leading term and the suppressed term. And one of the important things to note from this thing, this is the point which I want to make, is that the first term, there's no beta squared by r squared term in this expansion. So it's because if there was a log term in this non-trivial critical point, there would have been that term. But in this case, there is no beta by r term. And in fact, this is an important thing because, I mean, these authors conjectured that the sign of the first sign corrections, beta squared by r squared, for any CFT should be, greater, C1 is greater. That is the coefficient C1, they call it. And C1 is greater than or equal to 0. And in this case, it's very, it's at the critical point. Usually these Owen models, all these bounds, they saturate it actually. So they sort of, this saturates that bound, it is C1 equals 0. And the general form of the expectation value also fits in with the thermal CFT. You can see that it is the scale is there, R, 1 by beta cube, that scale. And then everything is a function of beta by r. So that structure of a conformal CFT on a sphere is there. And this method allows us to reconstruct this function actually, order by order in beta by r expansion. And another observation of the result is that if you look at this pressure, del Z by del V, it has this negative term, and which is correct, which should be the correct case for a bosonic system which is confined. the pressure first correction, finite size corrections are negative because it tries to pull together. So, so that also fits in. And it's also useful to compare it with the Gaussian theory, the free theory, massless theory. And you see that that has a beta squared by r squared, while this one doesn't have. And that is because of the log beta term, the partition function for the free theory. So, so this is sort of the things which we like. The first thing, the very first thing of solving the partition function. Just a bit time. Okay, yeah, I have 15 minutes. Sorry, I'm like going very slow. Okay, I'll try to sort of indicate very quickly the remaining results. So, so the higher, yeah. So of course, as I said, this theory has higher spin currents, higher spin symmetry, and at finite temperature, one-point functions of these higher spin currents. There are methods developed, and quite a few people have studied this method of evaluating one-point function of these higher spin currents in these models using something called the Euclidean inversion formula. And the method of the Euclidean inversion formula is like, given the 2-point function of the scalars, and you look at its OPE expansion, and each OPE comes with certain coefficients and certain higher spin currents, and to extract expectation value, you sort of you invent an inversion, a sort of inversion where you extract that particular higher spin currents expectation value. So so we, of course, these were done for the plane case, S1 times R2, and various situations, chemical potentials, fermions, and so on. Quite a few people have worked on it, and but we can generalize that method actually to S1 times S2, and by arriving at these one-point functions this way, which is slightly different from the partition function method, which gives you just the phi squared one-point function as well as the stress tensor one-point function. The phi squared is what gives you the gap equation and the stress tensor. So developing it this way actually gives us a cross check for that particular answer, and also a consistency check of the inversion formula. So it's good to do it this second approach also. And also added benefit is that you can actually get all the higher spin currents expectation value. And so there is a whole technology for that actually, and I think I will have to very quickly summarize it, but maybe some other time when when people are interested, one can think about it, talking more about it. But but it's there in the literature, and so essentially, because it's all these are higher spin, all of the totally symmetric traceless tensors, there's a particular form for the one-point function just by symmetries, and that is this form. And that is generalizable. In fact, the paper by Duffins and Mahajan and all those, they have done it for S1 times SD actually. So so that these functions become non-trivial functions of beta by R. So so it is of that structure, and this result is is basically because no tensors can get tensors with directions on the sphere cannot get expectation value. It's only in the time directions that they can get expectation value. So that's how this comes in. And for the ON model, when you take the two-point function, and you sort of expand it in OPE, the higher spin currents will be hidden in the OPE of this expansion of this 2-point function. And so the goal is actually we'll first have to derive the 2-point function, right? And then perform an OPE expansion. And term by term, we can do the inversion and and extract the highest spin expectation value. Yeah, so here is the OPE expansion of the 2-point function actually, and yeah, so it is organized in terms of some Kick-and-Bow polynomials. There's the way it comes about. But I think, given the lack of time, maybe it is good just to know that, yeah, you can just sort of, there is an OPE expansion, and these coefficients, these 1-point functions, can be obtained by doing certain integrals on the 2-point functions and extracting them out. So, yeah, so there is this OPE expansion, and in this case, because we are in the sphere, and we are trying to perform 1 by r expansion. This 2-point function is actually, in terms of the 2-point function, is in terms of the geodesic length. And one has to take this r going to infinity and keep the theta fixed to organize the OP expansion. So we do this OP expansion. So it is a short distance expansion, but in this particular way of limit. So it's near the poles. So we expand it in that form, and there is a systematic procedure. And then we can apply the Euclidean inversion formula. So by doing this, as I said, we'll get an independent check of the stress tensor obtained from the partition function, as well as the gap equation. And the stress tensor actually is spin 2. Out of the spin L's, it's spin 2, and the gap equation comes from the spin 0. So the crucial input again of carrying out this forward is basically the 2-point function of a massive scalar. And here it is, the 2-point function. Formally, I think any of us can write this down. You see, this is the so this is the Fourier transform analog, right? So there is the YLMs, product of 2 YLMs, which becomes the Legendre function, and this is the propagator. So this is analog of e to the power of I k x minus x prime divided by 1 by k squared plus m squared. So it's analog of that. So that's the propagator. Because it's S1, there is this part of S max square frequencies. And so then one follows the same techniques. I mean, you can sum over the Matsubara frequencies by a Poisson resummation. You arrive at this particular form. And then the difficulty is, of course, again, doing the angular momentum integral, which you follow the same strategy. I mean, you exponentiate it, and then you linearize it using the Hubbard-Stratton-H trick. And this linear sum, this particular sum 2L plus 1 PL cos theta into this sum, that's known in terms of a generating function, actually. That's known, and that can be written in this form, total derivative. And then there is a sequence of steps, I think, very similar to the partition function of arriving at that. So, I mean, once you do the L sum, there will be one integral which is left over, which is of this kind. And then you have to do some contour manipulation of this integral. And you can, once you do that, it's sort of so that integral is on one direction. And this was, again, the tricks for that, conformal fields on spheres. So similar tricks, actually. It's on this, and then you deform it deform this contour along the C prime. So there are some tricks of doing it, and you arrive at this nice expression, which is suitable for 1 by r expansion. So this form, for instance, it's immediate. You can check when you put mass equals 0. It's quite a non-trivial 2-point function. This is also not seen in the literature for a massive scalar on a sphere. This when you put m equals 0, this answer is the propagator of a conformal scalar on S1 r times S2, which was written by Fufu and Sachdev. So now, once you have this 2-point function, you can systematically do an expansion at large radius. And yeah, it's a mess. It's a systematic expansion in large radius. And here is the term, the flat space term. And then there is the systematic expansion. So once you have that expansion, and you can apply the inversion formula for each term, each of these 1 by r terms, you can expand. And there are certain analyticity properties. I'm sort of going in because, there are certain analytic properties which are satisfied, which need to be satisfied by the 2-point function, so that the 1-point functions can be read out. And that is true, actually. We have checked that it's true. And so to extract out, there are certain integrals to be done. I wouldn't go into the details of it, but there are some integrals to be done to invert and to extract a 1-point function. That all can be performed. And here is the phi squared 1-point function, which we have to set to 0 because that's the gap equation. And the thing about this is, okay, you can go to arbitrary spin, but you can go order by order, unlike the case of the partition function where you have all orders at one shot, but of course, minimizing, you can get only order by order. But in principle, the partition function expansion is still known to all orders. But here, order by order, we have to sort of do the inversion. And yeah, so here is the leading term. I've set beta equals 1 so that it's sort of simple to see. So leading term and the 1 by r term, and it agrees with the one which we got from partition function. And here is the spin 2, and then once you substitute the gap equation, it reduces to the stress tensor partition function. And similarly, proceeding this way, actually you can obtain higher spin, and in fact we have obtained the higher spin 1-point functions to the first 1 by r squared correction. We have obtained the higher spin 1-point functions, and in fact, so there is this observation which we have been doing over the series of papers. Actually, one of the observations is the following: that like if you take the 1-point functions of these higher spin operators and divide it by that of the Gaussian 1-point function, the free. So this is the non-trivial fixed point 1-point function of the spin L current to the free spin L current, and take the spin to infinity. If you do that, we notice that it goes to 1. So basically, higher spin operators, as the spin increases, it behaves more and more like a free theory. So it's free theory, though we are at the non-trivial fixed point. So we noticed this, and it was initially observed numerically, then we showed analytically later. The question is whether it's true for the next order correction also, because now we have that thing. Yeah, here is that observation for the original theory, S1 times R2. K basically is dimension. Oh, I have shown you a different. Yeah, K is different, but I mean, oh, yeah. So here is, yeah, you can look at K equals 1, actually. We have plotted it for different dimensions also, because we did that too. But you can look at K equals 1. That's this. And this is the spin, and this is the ratio. And K equals 1 is actually D equals 3. So it's 2K plus 1. That's the dimension. So you can see that quickly the ratio becomes 1. This is for the one model. This is for the one model in the other dimensions. This property is sort of true actually in the other dimensions also. So we want to see whether this property is true for the finite size correction also. So if you take this first order finite size correction to that of the free theories, finite size correction, and you can plot it. Okay, it tends to 1. I mean, you might think it's not, but it's like from 0.96 actually. So it tends to 1. And here we couldn't prove it analytically. So it's still numerics actually so far. So it is this, even the finite size correction, as you increase the spin of the operators, it somehow tends to the free theory. It'll be actually good to prove this, but we haven't managed to do it. So maybe I will conclude, and then I think then maybe we can sort of, if people want some discussions, then we can have some. That's why I thought of ending it a few minutes earlier. So the conclusion is the method developed for this obtained finite size correction for the larger and critical one model can be systematically extended to to higher orders. And it will be interesting to see actually the behavior of these observables, like partition of the energy density and so on, as a function of beta by r. Because I mean, of course, I don't think I expect a phase transition from this model, but still it'll be interesting to see how it goes from from this larger radius or plane to the r to the finite size. It'll be interesting because the expansion on the other side is different, and I think the groups at your side, so you guys have tried to expand it from the other side, in which the expansion has e to the power beta all the time. So, and the method can be used, for the other theories. For if you take large and vector models for fermions and S1 times AdS2, even for chemical potentials. Yeah, it's potential. You can generalize this approach to other cases also. Okay, this is the other case if you want to. So, but maybe I will sort of stop here, and because it's about an hour, and maybe then if people ask questions and so on, then we can have. Yeah, I don't know how it goes actually. I thought people might have questions, and so I can stop here.
Okay, thanks, Justin, for the nice talk.